Excellent. I am now also live. So everyone that's
Alrighty.
here, thanks for joining in. Tonight we are going to have Alan, Space Audits, presenting on the orders of measurement and experiment. And yeah, I've been looking forward to this one for a while. I got a feeling this one is going to be quite a doozy, pretty loaded, lots of very good information. So really looking forward to it. Go ahead, Alan.
It's
Whenever
going to
you're
be
ready.
necessary. Excellent.
All right, here we go. So this is on the orders of measurement and experiment. The purpose here is to go over the principles of scientific investigation, philosophy, and logic. So before we can start, talking about experiments and how to interpret them and what do they mean, we're going to go over some basics, so we can get a foundation for how to interpret these, for how I'm interpreting these experiments and stuff. So we'll get into that. So we often hear a lot about what is the scientific method, what are the rules, who's following it, what's that. So this is what I'm going to be following. This is my basic outline. So make an observation, define a problem, form a hypothesis, conduct an experiment, derive a theory. All pretty straightforward. All the basic stuff that we remember from middle school. Nothing too fancy there, right? So now that we have a scientific method to which we can apply, like we could apply a structure to for analysis. We'll move forward to the philosophical interpretation. So for the philosophy, I'm going to go with philosophical realism. So it's going to be focusing on accurately portraying reality without romanticizing abstraction. So it focuses on proof through logical deduction. So not making broad assumptions and then reifying it and retroactively changing everything and all that. So pretty straightforward. All right. So before we, now that we got our framework and our scientific method, we're going to learn a couple more concepts. We're going to learn about the orders of measurement and orders of approximation for mathematics and first order effects. So like when you can introduce something to a, when you can introduce a variable to an experiment and you get a directly proportional reaction to what you introduced, that's called a first order effect. So we'll get into that and the significance and how it relates to all this. So let's see. All right, okay, so we got first order experiments, first order mathematical derivations, and first order effects. Okay, so to get in a first order. So for a first order experiment, what we're going to be talking about, pretty much all of it's going to be regarding light. So we're going to be looking at light, how it travels in the path, right? So for most of these experiments, the setup is going to consist of an orthogonal setup where a light beam travels back and forth perpendicular to itself, or I'm sorry, orthogonal to itself, and then recombines. And then there'll be another setup called a closed loop setup. Now, in this setup, you can consider it like a round trip, or I'm sorry, like a one-way trip, so to speak. So you can have that configuration, like the square configuration here, in any configuration, and the way that it works out, that would be a first order experiment. Because instead of being like a round trip, it's kind of like a single way. So to kind of break that down, the significance of a first order experiment would be, to kind of give an analogy. Okay, so say you're at a starting point and there's a car that passes you by and you have a stopwatch and you take a time, or you start the stopwatch when the car passes you and you stop the watch when the car hits the finish line, right? So you have a one-way measurement, one point of source for the accuracy of the measurement. Now a two-way experiment with the there and back trip would kind of be like taking an average, right? So if you look at the left setup here, you see that the light beam is going back and forth. It's extending its the length of travel, right? So there's that back and forth relationship allows you to take like an average, so to speak, so you can get a more refined reading, and then from that you can get into, actually we're still on effects. Okay, so you can get a more refined reading, and then you can do further analysis on that, and you just kind of get more information about what's going on. So it's not necessarily that like one's better than the other per se, right? But they each have their own advantages and disadvantages to the types of experiment and the information that you can extract out of them. And the same goes for the mathematical analysis as well, which we're going to get into. But before we do that, we'll cover first order and second order effects. So a first order effect would be when you can introduce something and trace the reaction back to that with a proportional ratio. So that kind of comes back from chemistry. So just read here from this. Let's see. A first order reaction is one which the rate of the reaction is proportional to the concentration of the reactant. So that direct proportional relationship. So we'll get into how that relates to interferometry and all this stuff here in a minute. All right, we're going. Okay, so for the mathematical analysis, you can increase the order of approximations by squaring the denominator. So you can kind of think of that as like moving the decimal place back to get a more accurate, or not accurate, to get a more refined reading, like with a different ratio. So you can kind of analyze the same thing, but just at a different level, mathematically. So that's yeah. When you get into the ratios of these, right, you're gonna because this is classical mechanics, right? So you're gonna see V over C. So you're gonna see a velocity component ratioed against the speed of light. And the interpretation of that is that the speed of light, is changing, right? Now, what they tell us nowadays is that the speed of light's the same, it's a constant. That prediction that comes out of that is actually just basically describing the Doppler shift, the frequency shift of light, and not a physical change in the speed. But that's a whole separate issue. So let's see, you got that. Okay. All right. I had a video here to play, but I couldn't get it to play with how I'm presenting. So I'm just kind of recap. So this is Newton's bucket. So to kind of give a little recap, we have Isaac Newton. He has a thought experiment where he's got a bucket filled with water. And when the bucket's stationary and not moving, the water is stationary, not moving. So he applies his equations to the water. The water has no velocity, predicts no movement. So there's no curvature in it. And then when he spins the bucket, a force is applied to the bucket. It starts to curve. So from the lab frame, you apply the laws of motion and everything. You make the correct prediction to the bucket. Now, if you take an observer that's inside the bucket, that observer is going to see the lab frame spinning around him, and he's stationary. So his water velocity is going to be 0. When he applies that to his frame, he makes the incorrect prediction because the water is curved, right? The water has a velocity, but he can't tell. So we get into this kinematic and dynamic relationship where Newton found that there's an absolute frame of rest, but he just didn't know where to put it. So he said, maybe it's in space somewhere. So he attributed it to absolute space. Then Mach attributed the same thing to the stars, and Einstein came along and said, well, maybe it's with respect to space time or whatever, right? But there's no actual frame. But another way to interpret that would be that the lab frame is at rest, right? The only place where these equations hold true and can make predictions is when you're in an inertial frame, when you're at rest. So every experiment that's done somehow miraculously scales proportional to how inertial the Earth needs to be to conduct the experiment, despite the fact that they say the Earth is a non-inertial frame because it's rotation and all that, and motion through the cosmos. But somehow, miraculously, all these equations of motion only apply to our frame, and then covariantly extend outward, where every other frame needs to be backwards compatible with the rest frame. So it's like the implication there is pretty straightforward: is that the correct way to interpret the experiment, the correct way to interpret applying the laws of physics, is that we are at rest. All right, so that's and another one to touch on, another analogy that applies to linear motion is the hitchhiker frame. So Bennett's hiker, he came up with the hiker analogy. So maybe the Newton's bucket's a little like the rotation, like maybe it's a little unclear. So you could apply the same situation to Bennett's hiker. We have a hitchhiker on the road, stationary, not moving. You have a car coming towards the hitchhiker. The guy inside the car can use all the forces that he's feeling and make predictions and say that I'm actually stationary, and the guy that's on the road is moving towards me at the speed that my car is moving, right? That's a kinematic swap right there, right? But obviously, in reality, the hitchhiker's stationary and the car is moving. There's only one way to interpret that, and there's only one way where the mathematics being applied is actually meaningful, right? So our framework moving forward is going to be that the Earth is at rest, that the rest frame is here, right? It's not out in space. It's not out in the stars. It's not in space time. It's not in an abstract equation, right? It's a real place. All right, so that kind of went over the kinematic and dynamics a little bit, but to just recap on that, on the difference between kinematics and dynamics, we have kinematics cannot distinguish relative motion, dynamics can. Kinematics is focused on measurement and not the causal reason of why things are moving. It's just a measurement of the motion itself. Dynamics would be applying real forces based on that motion observed in the kinematics to try and make predictions on that motion to see if you can, solve it with real forces. And, then that's when your thing becomes a theory and a law and all that and starts progressing, right? Otherwise, it just flops. If you can't make dynamic predictions based on your kinematics, then it doesn't mean anything. Your kinematics don't mean anything. Okay, so proof by logical deduction here. So as we're moving on here, we're going to get into the concepts of the ether and how that relates and how that's intertwines in all this. So we need to get into how are we going to deduce there's a substance that we're getting effects from. We're measuring these things and we don't know what's going on. What's the logical deduction here? How can we interpret this? So if the antecedent for gas pressure is containment and it logically follows there must be a container. We all agree with that, right? So when the laws of physics, Newton's equations hold true, to this day they were derived in the lab frame, stationary, non-rotating. So all those equations that he came up with for motion were derived here on Earth, the ones that we still use today to describe everything. They weren't derived from different reference frames where the laws of physics could potentially be different and they had to be tested. All done in the lab frame. Everything's backwards compatible with a stationary with a stationary non-rotating Earth that has an absolute rest frame that seems to be ambiguous to those who have an inherent belief system that we're in motion, despite the fact that it can't be felt. Okay, so let's see. Logical deduction. We're in the stationary frames here. All right. And if we accept those logical deductions, that dynamics applies on real forces to make an analysis and make predictions and confirm reality, or it can prove a hypothesis false, can falsify it, then we must accept that the lab frame is true. And if we accept the lab frame, then the Earth's motion is a hypothesis awaiting to be experimentally verified. All right. Let's see. All right, now that we have our framework of interpretation, our logical framework, we've deduced some things, we've applied what we've learned, we've gone over the history, and we have a framework now. Let's start. Let's go interpreting the world or whatever. Let's go through the history of this. So I was going to insert a slide from Austin's Æther presentation about a false dichotomy, because the two frameworks presented are atomism and the Æther framework. So in the atomism, everything's infinitely disconnected. In with the Æther framework, everything's connected, right? So there's two possible frameworks. I'm happy to hear another one. I just haven't heard any, so feel free to hit me up with a different one. All right. So we're going to begin our analysis on the study of light, because this is where it all comes back to. This is where it all starts. This is what changed all of physics in 1887, the study of light. All right. So back in the 13th century, we have Roger Bacon, who split a. So anyway, we have Roger Bacon who split a light ray, or he noticed that a light beam had been split by a glass in his office or something, and it split into a color spectrum, and he was like, oh wow, that's interesting. So that's the earliest reported wavelength spectral splitting that I found. It's on record. And then we have Newton coming in, and he does his thing with prisms. So he does a more refined approach rather than just like an accidental happenstance or whatever. He takes some crystal prisms, splits light beams, and finds that the color is not contained, or that the color is contained in the light beam. So he split a white light into a color spectrum, and then he used another prism to recombine it into a white light. So there we did a little experiment, So we have a first order effect. A coherent light beam constructs or when split, gets split into different color wavelengths. So that's where we're at with that. So that was the first iteration of these wavelengths. So splitting light into wavelengths is going to become super important later on, because that's the study and basis of that is the foundation for everything. Okay. So we have Joseph von Fraunhofer in 1787 to 1826. And what this gentleman did is he picked up on the wavelength splitting that everyone was doing, Newton and all them, and he got down to business and really measured the wavelength. So using a similar setup to a prism, Fraunhofer made a diffraction grate, so it's just a really fine grate to split the light beams. And with that, he was able to take different sources, split like different colored light sources and different sources of emission, split those into a spectrum, and then measure the wavelengths and start categorizing all these things, right? So we could say like, okay, white light is this wavelength that produce, this frequency, that sort of stuff, right? So all this stuff was being systematically categorized and broken down, in the background there by different people. But some of the, this guy was a large portion of it, so I put him on there. Okay, so throughout the history of all that, we got all these wavelengths being detected and figured out, right? So I got the wavelength spectrum here, kind of go over that. So, and just to kind of recap, it wasn't just those three guys; it was a bunch of people. And at the end of the wavelength there, the end of the spectrum there, we have the X-rays and all that. So that was where Henry Becquerel, Marie Curie, Paul Villard, and Ernest Rutherford came in and did their radiation experiments using a lead cavity and all that. I kind of went over some of that in the Mount Meru presentation with the lead cavity. And you take a magnetic field or an electric field, and the coherent beam that comes out of the cavity from the radiated source will get split into different spectrums. So what they found is that radiation doesn't just emit radiation; it emits a gamma ray, a beta ray, and an alpha ray. And those have different degrees of charge potential associated with them. So this is what all these people were figuring out, in the 1700s to early 1900s, really, and just mapping this stuff out and categorizing it for it to be used later. Okay, so we have wavelengths that produce light sources producing light. We got sunlight, starlight, incandescent lamps, electricity, etc. When a coherent beam of light is split into a prism, it splits into 7 colors: red, orange, yellow, green, blue, violet, and indigo. When it's split into a spectrum, it can be recombined into its original color. The wavelengths and colors correspond to measurements in temperature, nanometers, millimeters, etc., and the wavelength itself. So I didn't cover this part of it, but during the spectrum splitting and analysis and categorization of the wavelengths and all that, they were also testing the temperature and all that of the different wavelengths. So like all that's like they really went hard on breaking that stuff down. Okay, so to recap, the observed phenomenon is a light beam being split into multiple colors. The problem or question would be: is the color inside the light beam adding color? Is the prism adding color to the light beam or not? And then with the dispersion and recombining of the beam, you found that the color is encoded in the spectrum, right? It's already in the wavelengths. Okay, so the experiment used that to recombine. The IV is the prism splitting for the splitting and recombining, and the DV is what happens to the light beam. Does it recombine or does it stay colorful? Right? Okay. All right, so now we're going to go over the history of the frequency measurements with Fazal, Maxwell, and others. So that was the wavelength spectrum. So that's the colors, right? Colors and temperature, that sort of stuff. So now we're going to get into propagation rates and frequency rates. Okay, so starting us off, we have ergo and the ergo effect. When a coherent beam of light is diffracted behind a sphere, the waves will recombine as they pass the obstruction, and their intersection point will produce a dot directly behind the spherical obstruction, radially outward from that intersection point. Yeah, radially outward from the intersection point, you'll see a fringe pattern of concentric circles. So this was done in, I forget, but it was like the 1800s by Arago. This was a really simple, this was a big reason why he was a proponent of wave theory, because back then they were like, is light a wave? Is it a particle? Is it a little corpuscle? They still weren't sure yet. It was still kind of back and forth, we're told. But this was a huge experiment, this diffraction pattern recombining here to make the sphere behind the physical obstruction really kind of solidified that light is definitely a wave, and it behaves like because of its wave-like behavior, right? So All right, so we have observed phenomenon, light producing a diffraction pattern problem. The diffraction pattern recombines behind the object. How can it be a particle? Hypothesis. If a sphere is placed behind a coherent beam and it diffracts, will it recombine such that it makes a pattern due to the intersection from the waves recombining? And then the experiment was, that's what they did. They played it out, and then the result was there's a sphere behind that physical obstruction where the waves recombined and intersected. So conclusion, that was Arago's line of logic for going, okay, light's definitely a wave. And then from there, he started to do further experiments, which we'll come back to here. So for the frequency of light, we have C equals lambda times F. So this is and F is the propagation rate, the rate of induction. So that speed that we're all familiar with, that's the excuse me, that's the frequency. So what we're looking at is the wavelength that they've been measuring, right? All those color spectrums and wavelengths that they've been measuring. That times the frequency gives you, the speed of light, object, right? So that's how they did it. So lambda is the wavelength, the distance between the successive peaks or troughs of a wave that's measured in nanometers or meters. And the F is for frequency, and that is directly proportional to the speed of light. So that's the number of cycles or oscillations per second. That's measured in hertz. And lambda and the frequency share an inversely proportional relationship where the wavelength increases and the frequency decreases, and vice versa. Okay. So now that we've got the frequency, we'll go down to we'll go over how they measured the frequency, and we'll pick it back up with Arago. So Arago's famous for two things. One of the things was that he thought that he would have to adjust his telescope's focal length when observing stars, at a certain time of year, and then 6 months later, instead of being in the direction of motion, we'd be we'd be looking at the stars going away from us. So he was thinking, oh, you know what? We'll probably have to adjust the old focal length there to keep those in focus. Turns out not necessary. Didn't have to do that. And then the other thing that he's famous for was in another experiment that he did, he half covered his telescope with a prism, and the idea there was that if the Earth was in motion, that the refraction rate of the starlight coming through it would, like, the angle would change, and it would cause a diffraction, or it would cause refraction in the starlight. So he was trying to observe that based on Earth's motion, and that was also a unnecessary. It produced no result. So he's quoted here: Arago's half covered his telescope with an achromatic prism. He found that the aberration of light angle was independent of whether the light passed through the prism or not. So it didn't, and what that means is it didn't matter. The Earth isn't moving. Like, the cause and effect relationship that he was trying to establish there wasn't substantiated. And if his experiment kind of sounds familiar, like Airy's failure, well, that's exactly the line of process that was continued off of it. So no motion or no corrections were required. So no motion. So we have Fazal in 1849, using his experiment in math, he derived a proportional velocity relationship using C in the rate and its induction rate based off of the interference produced by a rotating cog. So what he had here was a light source, and he was shooting it through a cog that was rotating at a fixed speed, and it was hitting a mirror, and he was basically counting the flash rate, like how many times light would flash through that, or how many times there would be like a pulse, over a period of time based on that rotation rate of the cog. And through that, he was able to deduce, like, the speed of light in 1854. Okay, so the observed phenomenon, light's propagating at some rate, problem or question. What is the induction rate of light? We know that the wavelength changes when the medium is introduced. Does the frequency change? Additionally, when it's moving through a medium, is there some kind of refraction index so that we can deduce that? And then, so hypothesis: Can you deduce the speed of light in frequencies using a time interval and a fixed rotation rate of when like how fast it would have to be, how fast light would have to pass through the cogwheel to produce that frequency that you measured based on the time, right? So that was the hypothesis, the experiment, and he conducted exactly that, and he measured it. So the successful experiment seems to render the adoption of the Fresnel's hypothesis necessary, at least the law for which the expression was alteration by the velocity of light of a body in motion. So actually, I think that's the wrong quote associated with that. So my mistake on that. But yeah, measured the speed of light based off of the pulse frequency of. Okay, so continuing on, we have referred to Arago's telescope and prism experiment that proves the Earth doesn't move because it was a null. There was no effect of refraction through the starlight through prism. Orange color seems to be possible to determine the direct speed influence on bodies. Okay, I think I was supposed to read this whole thing, or read some of it anyway. So let's go. Seems to be. Okay, so this is from Fazal. He says, one second. At the present time, we are unable to present yet. Hang on, I don't have my glasses on. Sorry. All right. At the present time, we are at the present time unable. We are at the present time in possession of means of observation of such of extreme delicacy that it seems possible to determine by direct experiment, what the real influence is of motion of bodies on a. Oh, okay. Sorry. So after we've got our we've got our frequency, we've got our wavelengths, we've got all that, right? So as they're doing all that, they started realizing that they could measure they could measure actual velocity with light, that there would be a proportional change. So this is the segue into the Fresnel drag experiment. So they're saying that like this is the first interferometer essentially, right? So when we go over the Michelson-Morley 1887, and they're like, oh, how did we get into that? Or like, how did they just randomly decide to do that with their crazy device contraption that they made? Well, it's all based off of natural science that in a long history. So this was the baseline for the interferometer. So the orange color, orange. It seems to me possible to determine that by direct experiment the real influence of the bodies on the velocity of light. Green, thanks to Arago for helping us with the refraction indexes of the interference patterns produced thereof, so we can deduce the fringe pattern produced by the velocity of a moving body. So yeah, that was super important. Coming up with how these wavelengths change with refraction when they interact with another media. So this is how they figured out like refraction rates and how it's affecting the frequency, right? The oscillation rate of light. So when the frequency rate changes, that's them saying that the speed is changing. That's how they used to talk about it. So, all right, and then so we're going to get into an experiment here where the absolute velocity of C was measured by using the displacement produced by refraction. So this is the Fresnel drag experiment. So we have the sunlight coming in, being focused in with a collimator, and then it hits a beam splitter. It hits it, which goes into a closed loop setup. It's recombined over here at the other end. And when the light recombines, it's out of phase. So it produces a fringe pattern. And what they found is when they measure that fringe pattern, they can get a proportional velocity relationship out of it. So they take the known speed, like what they measured earlier, like the fixed speed of C, right? And then they're breaking it down. They're reducing it with the refractive index of water. So there's going to be a fringe in that regard, but the water is also moving and has its own velocity component. It's flowing, right? So what they found was, in addition to the refractive index change, there's an additional fringe created, and it's proportional to 44% of the velocity of water going with and going towards the water. So there's an 88% total velocity component added to the water going with and against, and that's that was used as proof of the hypothesis that there's an ether that's being dragged by material media. So the way that they look at material media, so water is comprised of molecules, and they're saying that the molecular structure of water as it's moving through the ether is kind of dragging some of the ether with it. So electromagnetic propagation that's happening in the water, like right next to it, etc., is being dragged a little bit by the ether. So it's catching like a little speed boost, and that's the That's how they looked at it, right? That's their understanding of it. So that was all done with sunlight, mirrors, and prisms and water, right? So the super can't get any more natural than that. So observed phenomenon, light behaving like a wave, diffracting and recombining it to make interference patterns. Problem: there's a change in the wavelength when light's propagating through a medium. Does the frequency change, or does the speed change, or is it just some crazy relationship where it looks like the frequency changes but the speed's always the same? Could we use the moving media to see if there's a translational speed affects the propagation of through media? So hypothesis: there will be a translational speed gain observed in light as it propagates through moving media. There will be a boost that will likely be Galilean, meaning that there will be a velocity addition. So, and that the refractive index, there will also be a change to that experiment. So we already went over the orientation of it. So we got the focused light beam from the sun, beam split going with and against the water, recombine to make the fringe pattern. That when they do their math on it, they can deduce the velocity of the moving water, like as a component from the fringe patterns. Like they have a direct proportional relationship. So we have a first order effect, a fringe shift produced by a velocity component, first order measurement. That measurement is directly translatable to the experiment, and it has affected the speed of light in such a way that it's produced a fringe shift pattern proportional to that velocity. And that's also our dependent variable. So like the way that the pattern produced by the independent variable is introduced. And let's see, okay. Oh, so I don't think I went over the IV. The IV on that is water. So like the refractive index and the velocity of the water. Okay, so you could increase the flow, like the speed, right, to see how that affects the interference patterns, and you can take a differential off that, figure out the exact amount that the velocity is affecting it. So that's probably how they came up with their 44% ratio here. So then we have Maxwell putting everything to paper, everything that was being experimentally done and regarding electricity and magnets, mostly regarding Faraday and all that. So using math, he put together that the speed of light is 1 over the square root of epsilon times mu, which is the electric permittivity and the magnetic permeability in a vacuum. So they did electromagnetic propagation in a vacuum. They pumped everything out, and they found that there was still an impedance. So these are the lowest level values of impedance, like in a vacuum. So when they say, "Oh, the speed of light in a vacuum," well, they're referring to this derivation here from Maxwell's equations. Okay, let's see. Showcasing the rate of induction. So yeah, this again, this has been just a really accurate prediction on the rate of induction for C. You can use this to make a lot of accurate measurements, and it is the induction rate, right? So, all right. So that's a cool story, but hasn't the ether been falsified, right? We just went over the scientific method and philosophy and logical deduction and all this stuff, but hasn't the ether been falsified? Well, it's only been falsified through mathematical reification that can't be substantiated in terms of electromagnetic theory, like Maxwell's displacement current term, which was a term that was added to reify that an accelerating electric current can self-induce a magnetic field without a charge potential to create that. So it's just a self-reification fallacy built into useful mathematics that allows people to describe the phenomenon verbally without having to address the fact that there is a charge potential that's allowing that the induction of that field. Okay, so let's see. So, and the frames of interpretation of the ether that were debunked throughout the historicity of all these experiments and whatnot are in regards to a stationary ether and a moving Earth. So, like, these are two components that are pivotal to the ether theories that of the past, because if the ether wind's moving and the Earth's moving, you can't make it like it. They can't make any determinations off of anything, so they had to remove one or the other, because there is a directly proportional velocity relationship that's measured in the speed of light, which we'll get into later, that needed to be obfuscated because it directly refuted the motion of the Earth. So, We'll continue on, some title. All right. So we have naturally observed phenomenon of light behaving like a light. Or I'm sorry, light behaving like a light behaving like a wave. We have first order effects in the measurements of this behavior. So we could influence the light, like its propagation rate and stuff, with motion through refractive indexes, introducing different media. And we measure that rate changes. Right. So let's see. So failing to know the historical narrative on all this is exactly how you get tricked into, believing Wikipedia when it says, XYZ experiment disproved this about the ether, and it somehow proved that the Earth is in motion, even though it did no such thing, because you're not going to know the history of the importance of the fact that they've known for a really long time that you could split a light beam around a circuit, have it recombined, and it'll produce a fringe pattern out of phase proportional to the velocity of what the apparatus itself is on, or what you're introducing in terms of like refractive media that's moving with the Fresnel experiment, right? And you'll just kind of believe it. You'll just believe what you read without understanding the causal underlying mechanisms of everything, right? So it's that background medium that will have first order effects on electromagnetic propagation. And through experiment, we'll go over the first order measurements and of that material background medium that's necessary for electromagnetic propagation to take place. So as we're following the scientific method earlier, I'm also going to propose a model of ether for us to interpret, right? So we're done with the stationary ether models, right? We're now moving on to an ether wind model with respect to a stationary Earth. So if this is true, if this is a real mechanism, a real material media, it's going to have actual effects that can be measured in reality, right? So we can use this framework to logically deduce the existence of the material media, if not if not directly, indirectly by logic, right? So we have the anisotropy effect, the height effect, and the space effect, and the hydroaerodynamic effect. So in the next couple of slides, we're going to break down what each of these means, and then we're going to go over interferometry. So the anisotropy effect is the velocity of electromagnetic propagation depends on the radiation direction, or the direction that it's going, right? And it's stipulated on the relative motion of the solar system, the ether, the medium responsible for the electromagnetic wave propagation. So this is from Atsutovsky's ether model, and this is the what do you call it? Like the criteria for it. So in other words, there's a preferred direction for electromagnetic propagation, meaning it'll go faster east or west, and vice versa, and that'll be independent of rotational effects. So if electromagnetic propagation is occurring perpendicular to that flow, there'll be no variance gained, there'll be no speed boost gained or no reduction. The components or the variance will only be caused by the east-west directionality, there'll be no speed boost gained or no. All right, the height effect. The velocity of wave propagation depends on the height above the Earth's surface. That is stipulated by Earth's surface interaction with the various ether streams of material medium that is responsible for electromagnetic propagation. So the height effect, or the what do they call it? The altitude effect, is electromagnetic propagation will be higher at altitude, right? So on a spinning globe with no ether components or anything like that, under the paradigm that they give us, as you get higher in altitude, the speed of light has to be the same, can't be different. They have certain ratios that are derived off of the constancy of c, like stellar aberration, for example, where they derive a 30-kilometer velocity out of an angle using the ratio of c. Now, if the speed of light changes at altitude, well, that ratio really doesn't mean anything, right? So, if there's a change at altitude, that's a huge deal. That'll lend more credence to the fact that there's a material medium that's carrying a translation of motion that's coming from the sky. We'll get into that in the next slide here. So we have the space effect. The velocity of wave propagation changes due to the period of one stellar day that is stipulated by space or a galactic origin, right? The medium responsible for the ether, that the periodicity measured within the fluctuations of the speed of light when measured and plotted against sidereal time will show a cause and effect relationship where the periodicity will reach its minimum and maximum dimensions according to sidereal time, right? So that'll show that the fluctuations are coming from space, right, from a galactic origin, and not coming from the Earth rotating or moving, right? So we have the hydroaerodynamic effect. So the velocity of electromagnetic propagation will behave differently, and it will obey the equations that describe fluid dynamics, essentially, right, in gases. So when you apply the equations that solve for how fluids interact with Fermi surfaces and dielectric insulators, um, how the laminar flow and turbulent flow interacts with that. He's saying that you'll be able to measure in the speed of light some sort of relationship where the material medium that's responsible for the electromagnetic propagation is going to be behaving in a way that's responsive to the equations that describe fluids and gases, and that's going to cause light to change accordingly. And he's saying that you can measure that interferometry through interference patterns produced by the irregularity of that motion of the material medium, which is necessary for all electromagnetic propagation to take place. And Fermi surfaces are conductors. They're usually metals or otherwise conductive materials, and a dielectric insulator is any material that stores electric capacitance. Okay, so we have James Bradley with stellar aberration, which I already went over. So to give a quick recap on that, suppose starlight's coming down parallel as one does, and the Earth's rotating around the sun. They're saying that over the course of a year, there's an aberration that's produced by that. So this is a great example of kinematics. This is a measurement. It doesn't tell us anything about if the Earth is moving or if the stars are moving, right? Because if the ether in between us and the stars is moving, then there's going to be an aberration, right? So the angle relationship that they derived and all that, and the story that they tell about it is kinematics. That is kinematics. And remember, guys, can kinematics distinguish who's moving? No. So we have this cool velocity angle relationship, but does it mean that the Earth is in motion? No. And this was a well understood concept back in those times too, because nowadays everyone just kind of reifies it, talks about it like it's like this kind of measurement is direct proof, but it wasn't in 1898. A guy named Willem made a posted in a physics journal or whatever, like analyzing 10 experiments that proved that the Earth, that gave a null result for Earth's motion, and one experiment that gave a positive result. Well, the positive result mentioned is Bradley's observation of stellar aberration, but he even notes, like the Wilhelm, he's like, hey, this is the only positive confirmation we have, but this is a kinematic measurement, and we really need other things to substantiate it. So everyone, like, this was a known thing. You see a thing in the sky and it does something mathematically, it doesn't necessarily mean that's the reason, right? So they're kind of stressing the importance on this because kinematics and measurements, a lot of the heliocentric model, pretty much all of it, is reified through kinematics. So that's why it's important to go over. So we're going to get into Airy's failure now. We're going to start covering the experiments that use light to measure motion in regards to everything that we just learned about light, how it interacts with material medium, and how you can get velocity relationships out of it and all that. So we're picking back up off of where Arago left off now. Remember the guy with the telescope and the prism who found that there was no need to make any adjustments either way because the Earth isn't moving. So later, Airy came along and was like, hey, if we have a telescope, an empty telescope, and we have to correct it let me back up a little bit. So part of what this guy, James Bradley, noticed with these observations for stellar aberration was he had to correct his telescope to 90 degrees so he can get his observations, right? And what he found is when you have a telescope 90 degrees, you actually have to tilt it forward slightly because the starlight comes in off angle for some reason, right? Now they attribute that to Earth's motion, right? Now, let's see, we're going to get into how you could test that, right? Because this is just kinematics. How do we do an experiment to show a cause and effect relationship? So if we have an empty telescope on an Earth that's moving, at 5 miles per hour, say, right? You're gonna have to correct your telescope from 90 degrees, 5 degrees, so that you can get that starlight to come into the center of the telescope, right? And if the sky is moving and the Earth's stationary, same situation, right? You can't tell anything from that. But if you fill the telescope with water, now the light's going to be slowed down and you're going to have to compensate now. So if the Earth is moving and there's now a refractive index or a refractive medium introduced into there, light's going to be slowed such that it's not going to come in the center anymore based off of your 5 degree angle. You're going to have to tilt it forward additionally to get it to come into the center when there's a medium in there. And if the Earth isn't moving, if the starlight's already coming in at a 5 degree tilt because of an ether drift, right? Then when you put the water in, you're not going to need to correct it. You're not going to need to tilt it any further. So let's see what happened. So let's do a quick recap here. Okay. So, okay. All right. So, recording this, what happens when we introduce the water, that angle correction relationship is going to tell us who's moving, right? This is a super straightforward experiment. There's no refutation to it for heliocentrism. There's no relativistic explanation for it. And that would have to be provided because that's the current paradigm. This experiment is so straightforward and simple that it's almost too straightforward where you're like, am I misunderstanding? Is it really that easy to where you'll just gaslight yourself and give it up? Don't give this up. This experiment proves that we're stationary. The Arago experiment also did. This is a continual history of stationary Earth experiments where they've introduced. So we took the telescope with nothing in it, no variable. We introduced an independent variable, the water, and we found that it didn't require an additional correction angle, right? So the dependent variable, the correction angle that would be produced by the would-be motion that we could deduce from that, it doesn't exist. Okay. All right. So this is the data from that experiment, and we'll often hear, the Aries failure. He failed to measure Kirkle-Fuse's ether interpretation. No, don't get gaslit. It's not what happened. Well, that's part of what happened, but he didn't. The thing was in regards to the Earth's motion, though. So. Because we'll get into the correction angle that would have been necessary had the heliocentric model been true, because this is truly pivotal, right? So we have the data for the observations here. We have 51 degrees, 21 minutes, 34.4 arc seconds, right? And then for the other observation, we have 51 degrees, 28 arc minutes, 33.6 arc seconds. That's a difference of only 0.8 arc seconds. That's not even an arc second. It's fractions of an arc second. So those the correction that he had to make was so minuscule, it's not even an arc second. And so what was the heliocentric prediction? Had it been retained, the aberration employed in the correction would have been increased by 15 arc seconds and minus 15 arc seconds respectively. This would mean the results would have agreed by 30 arc seconds. So they would have had to make a hell of a correction compared to 0.8 arc seconds, right? Heliocentrism isn't even on the table anymore. That's crazy. So, and they'll try and tell you, this was about Huffle or clinker fuses. Nah, man, it was about the motion of the Earth. Simple, very, very simple and straightforward. How do you test this kinematic relationship to deduce if the Earth is in motion? If starlight requires an additional correction angle, then the Earth is in motion. If it doesn't, the starlight's already coming in with a drift to it, and we're stationary. That's it. Very simple. All right, AI image. So there was supposed to be an image here to kind of recap on what I just said with the Aries failure. So you can go ahead and call it Aries success if you want. That's what I would do. So this is a first order measurement. The starlight's coming in one direction. It's taken on a one-way path. And it's evidence for an ether wind, right? Because there actually was a slight displacement that needed to be accounted for. Very, very slight drift. Well, that's in line with ether drag, right? That's in line with the ether theory. There's no space-time drag, right? So Aries success, if they already knew that light propagates slower in a medium, then then this was experimentally shown that that the Earth isn't moving, man. So very, very straightforward. All right. So we know we've deduced that we're stationary. We've deduced that the speed of light changes in refractive media. We figured out that you could measure proportional velocity relationships with the speed of light using interference patterns, and based off of those mathematic predictions, with Maxwell regarding the induction rate of C and all that stuff. So we have a really solid framework of interpretation of a stationary Earth relative to an ether wind. So, all right, let's continue on now and start analyzing interferometry. So we have the 1887 Michelson-Morley setup. Here's a little cartoon graphic of what the apparatus looks like. The actual picture that you see isn't very good. Isn't like the lighting sucks on it, so I don't care. I use the cartoon picture. So here's a topographical view of what the beam path would look like. All right, so it's going to hit this mirror, reflect back. Also, when it hits the other splitter, it does the same thing, recombines on its path back. So this is a there and back relationship. This is a second order setup, right? So this is going to be earlier how we talked about kind of averaging out a reading, kind of increasing the sensitivity of it, so to speak, so that you can measure finer, so you can further break down and analyze periodicity within a first order measurement. You can break it down further by doing that kind of stuff. So this is the setup for that. So the math here that they use, this is a second order approximation here. So, and like I said, they were trying to increase the like their ability to make approximations, the magnitude of their approximation. So that's where they use the second order squarings. So they do this to get, okay. So we have V, the velocity of light. So that's the C that we're all familiar with. V, the velocity of Earth's orbit. D, the distance of propagation. So in this setup here, it's the distance from the source to the what do you call it? The microscope, where it gets recombined and you measure your interference pattern. So the distance traveled as if this was all one big distance. So that's your distance component. And then your time components, and those all reduce down. The time components cancel out. Everything reduces down. So in the simple form, you get 2D V squared over V squared, which is the velocity, the assumed velocity of Earth over the speed of light, and that's going to give you the prediction for how much fringe will be displaced. How much of a fringe shift you'll get based off of the 30 kilometers a second orbital velocity that they need to confirm heliocentrism. So this is how they derive that relationship with light to make the predictions with everything. All right. So, and remember, this isn't just like some willy-nilly, oh, this might be what it's like. No, this is very precise methodology in mathematics based off of relationships that have been already figured out years ago. Give me 1 second.
Yeah, that's really fantastic. What is the source on that one? Because that's a really fantastic breakdown of that math.
Oh, that's from the Michelson-Morley paper, bro.
Oh, thank you. Fantastic.
Yep. Okay. And then, so they go on to say here, so hypothesis, right? If the Earth is in motion, when the interferometer is aligned with the direction of motion, the orthogonal arm will be dragged against the ether, and the variance will be proportional to the speed of light when it's measured, when the wavelengths are recombined. It'll be out of phase. So the independent variable is white light. So because they need their wavelength to get their fringe as well. So the wavelength that they use, the orientation of their apparatus. So and they do measurements at different times of day, because remember, they're trying to measure a motion that corresponds with sidereal time. So part of the apparatus alignment is going to be like when you're taking the measurements throughout the day, right? So that it's actually aligned with sidereal events, Okay. So we have here the fringe shift pattern produced, predicted, and the amount measured. So the dotted line represents the predicted amount, and the the solid line is the amount measured. So just under one fringe. So the dotted line is the theoretical curve. Conclusion: the Earth's relative motion to the ether must be very small. The fringe displaced is proportional to a velocity of 6 to 7 kilometers a second, or 13,400 miles per hour. So there was a velocity component measured proportional to the fringe, right? As according to all of the, I'm not going to go all the way back, never mind. As according to all the stuff that we covered earlier. Okay. So what do we do now? What do we do now? Because we got a whole history of null results of the Earth in motion, and we just took a really big one, kind of combining years of knowledge on the history of light and how it works and how that relationship is derived mathematically and physically, to get the fringe patterns, right? So this was a huge experiment for the for physics and heliocentrism, because this was going to be confirmation of the Earth through the cosmos, and didn't get the fringe at all. So if this fringe isn't 30 kilometers a second, then there's no measurement of Earth's velocity, because the velocity component is a first order effect. It produces first order effects in measurements, right? Second order or otherwise, there's going to be a component that's proportional to that velocity, and it's not there at the magnitude in which they need it to be. And so the reason why they redefined all of physics after this experiment that lasted only 6 days was because the implications were insane. Like, people that knew the history of this and knew how all this works were like, oh, like that, like, what do we do? So they had to come up with, different ways to describe ether contraction was around for a little bit. But let's kind of get into the fixer situation, and then we'll continue on the history of interferometry, and we'll kind of compare ether to the relativistic framework to see which ones hold up. Okay, so the reason that all of physics was redefined over this experiment was because of that proportional velocity relationship. As we continue on, the same equations that are used to measure first order effects in angular velocity and linear velocity will be used to derive velocity. And then they just say, for some reason, we can't detect the Earth's motion. Although the orbital velocity around the sun is not detected, the orbital circumference is too big, or is so big that the curved portion of light might as well be considered linear. So from this point on, the orthogonal or right angle interferometer setups that have that there and back perpendicular, orthogonal setup, were said to be unable to measure linear motion, and that the variance in C produced by the fringe was actually rounded down to 0 later. They said, well, it's actually no fringe. We'll just go ahead and say that it's none. So so from that, they said, okay, well, the speed of light must be constant, right? And there's no change in it. So we can't use it to measure linear velocity, because they knew that they could use it to measure velocity, but just not linear, now that it didn't give the measurement that agreed with their with the Copernican principle. So Einstein's theory of relativity was put forward as a solution to this, and using Lorentz transformations, an entirely new framework of mathematics that exists only as second order effects of length contraction and time dilations, are put forward to explain first order velocity effects that are measured in the first and second order experiments. Through the relativistic transformation, the first order velocity effect of 6 kilometers a second is reified through the second order effect of length contraction in the apparatus that has to contract proportional to the assumed 30 kilometers a second. This is an unfalsifiable premise that the contraction happened in the frame before the measurement even takes place, because it's already in motion. So you've already been contracted before you were even born, before you could even take the measurement or conceive of contraction. It's already happened. And that gamma factor contraction ratio can explain the missing 24 kilometers a second, which gives the appearance of an actual explanation as to why the Earth's motion couldn't be measured. And once you have people accept that framework, you can retroactively explain almost anything, especially if people don't realize the history and significance of these measurements and where they came from. Okay, so we're going to read now from the principles of, from Einstein's special relativity paper on the electrodynamics of moving bodies, 1905. So this is going to be the jumping off point for the framework of interpretation known as relativity, special relativity, right? So Einstein says here, examples of this sort Together with successful attempts to discover any motion of Earth's relative velocity, the light medium suggests that the phenomenon in electrodynamics, as well as mechanics, possesses no properties corresponding to the idea of absolute rest. They suggest that rather that they suggest rather that, as has already been shown in the first order of small quantities, the same law of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. We will raise this conjecture, which will hereinafter be called the principle of relativity, to the status of a postulate, and to introduce another principle or another postulate, which is only apparently irreconcilable with the former, namely, that light is always propagated in empty space at a definite velocity c, which is dependent on the state of motion of the emitting body. Which is independent of the state of motion of the emitting body. These two postulates will suffice for the attainment of a simple and consistent theory of electrodynamics of moving bodies based on Maxwell's theory for stationary bodies. The introduction of a luminiferous ether, quote unquote, will prove to be superfluous in so much as that as the view here will be developed will not require an absolute stationary space provided with special physical properties, nor will it assign velocity vectors to a point in the empty space in which electromagnetic process took place. So this is going to be super important here. So before we continue, actually that's the wrong slide. We're good. So newly proposed theory. We're not going to use absolute space to invoke anything, and we won't assign imaginary vectors to a point in space in which electromagnetic propagation took place. And then we have here one more. We have, let's see. It is at once apparent that this result holds good if the clock moves from A to B in any polygonal line, and also when A and B coincide. If we assume that the results proved for the polygonal line is also valid for a continuously curved line, then we arrive at the results if one of two synchronous clocks at A is moved in a closed curve with a constant velocity of light until it returns to A, the journey lasting t seconds, then by the clock which has remained at rest, the travel clock on its arrival at A will be slowed by 1/2 t v squared over c squared slow. So this is the time dilation coefficient here. Thence, we conclude that a balance clock at the equator will move more slowly by a very small amount than a precisely similar clock situated at the poles under identical circumstances. So in there, he's essentially describing a light clock, right? So he's essentially describing an atomic clock in 1905 before they had an atomic clock. And he's describing like an orbit of GPS essentially, right? So they say GPS satellites are free falling around the Earth and there's an atomic clock attached to them. So this light clock, this bouncing back and forth oscillation to keep time is what he's referring to. And he's saying that they'll be out of sync in proportion to a time difference experienced that's a time difference that's caused by the velocity component of the moving clock. And he gives the coefficient by how much it'll be out of sync with, right? Okay, so let's see. Oh, and the important part to note here about where do the Einstein's equations hold true? Where's this framework where do these postulates apply, right? Well, they apply in inertial frames. And what's an inertial frame? Well, if a closed polygonal circuit in uniform rotation, that's an inertial frame because you can extend that out to infinity, and you can basically say, well, any point traveled along that is linear, right? There's not going to be much deviation, and that was the jumping off point for how he explained the orbit for heliocentrism, right? He was like, well, you can't measure linear motion anyway. It's actually traveling along a geodesic. Everything's on a geodesic. It's curved, but it's just some linear path, right? So this was the whole framework of where these equations apply. So if you're in a uniform rotation, you're in an inertial frame, according to what Einstein just said here in his 1905 paper. So Sagnac was in 1913, continuing the interferometry experiments, was like, okay, so I got your inertial frame, I got your uniformly rotating closed loop polygonal circuit. So he has a rotating device here, has a light source, 4 mirrors, and a photographic plate. The light source it's a half silvered beam splitter, gets recombined clockwise and counterclockwise, and on the recombine, it's out of phase proportional to the rotation of the device. So in relativity theory, they say that the speed of light is constant for an inertial observer. So if this uniform rotation constitutes as an inertial device, an inertial frame, there should be no fringe shift pattern observed. The speed of light recombined should be in phase. But there's a displacement, meaning that the beams are slowed down proportional to the velocity of the rotation. Well, I'm sorry. One of the beams, the beam that's going with the rotation is sped up, and the beam that's going against the rotation is slowed down, exactly proportional to the velocity of the rotation. So this is a first order effect in motion, or I'm sorry, a first order effect of motion being measured in an inertial frame, right, as constituted by Einstein. So continuing the experiments using motion, Sagnac in 1913 used a uniformly rotating platform and came along and showed us that the speed of light is not constant in an inertial frame. True to the specifications of relativity theory, in his own words about the uniformly rotating platform. So that's why Sagnac had a very specific title for his paper about how he proved the luminiferous ether through a uniformly rotating platform and all that. So we're going to look at the math here. Look at what he's using here. So this is a first order approximation, right? So first order derivation. The fringe shift this is a first order effect caused by angular rotation, right? So direct cause and effect relationship to the fringe shift is proportional to the velocity, right? And the dependent variable would be the fringe shift that's produced by the movement when compared to when it's stationary. So very simple, straightforward premise there, and it should definitely apply to Einstein. What do you guys think Einstein said about this? Well, he never commented on it, and he let the boys handle it. So we'll just continue reading. So we're going to close out on Sagnac's interpretation of what happened, or what he was measuring. So it says here, the optical effect measured from the fringe spacing, the displacement z on the interference centered that I observed with the preceding method in a particular case of the optical rotation effect that I've defined earlier in this book. Let's see, which the context of the current ideas should be constructed as a direct observation of the luminiferous ether. In a system moving as a whole relative to the ether, the propagation times between any 2 points of the system should change in a way similar to a stationary system subjected to an ether wind, the relative speed of which at each point of the system will change by the same directly opposite of the speed at any point, and would contain light waves in a manner similar to atmospheric wind carrying sound waves. The observation of the optical effect of such an ether wind relative to the stationary ether would constitute a proof of the ether's existence, just as the observation of wind relative to the atmosphere on the speed of sound in a moving system would constitute, everything else being equal, a proof of existence of a stationary atmosphere enveloping the moving system. Okay, so the interference pattern displaced by the constant fringe for the value. Okay. Weird. Okay, sorry. I was supposed to get just this top, or this bottom part. Turbulent air produced by the interference of the turbulent air produced by the interferometer by a fan rotating on a vertical axis and blowing downwards does not seem to produce any displacement of the interferogram's center, given a careful superposition of the 2 opposite beams. Any turbulent airflow analogous is and less intense, producing the rotation effect does not affect the experiment. So the air isn't being like drawn around in a vortex that's somehow producing this effect or anything like that, right? So the observed interferometer effect is that I'm saying the observed interference effect is much is very much the effect of an optical rotation due to the motion of the system relative to the ether, and that directly shows the evidence of the ether, a necessary condition for the luminiferous waves proposed by Hudgens and Fresnel. Okay. All right. So we got the um, so we got this experiment done. We got this rotation effect. We got a first order velocity component measured, first order measurements, first order approximation analysis of it. Definitely. So what he's describing there is like, so you know how they say the Earth's rotating or the atmosphere is like entrained with the Earth, but there's wind within it. So like that's kind of what that's how he's describing the ether wind, right? Okay. So before we continue on with the what is it? One second. Before we continue on with the time difference here, because they're kind of talking about time differences and time being different stuff. So we're gonna touch real quick on Einstein's how he describes time there. So special relativity, as stated by Einstein, states that a clock will be slowed by one half its fixed speed times let's see times its times the time of times t times v squared over c squared. And t is the time of the event of how long it's traveled or whatever, right? So this equation be used to describe the desynchronization between a stationary clock and a moving clock, the same way that the Michelson experiment derived a proportional velocity using 2d v squared over c squared, right? And we'll come back to that clock synchronization thing later, because that turned out to not be correct. But for now, let's focus on the important part, on how Einstein derives the inertial frame for the closed loop. And if c is constant, then there should be no fringes could be derived in the equation. So the equation that Einstein gives us can only explain a Doppler frequency shift that's proportional to the velocity of light as a second order effect. It can't actually explain the fringes being proportional to the velocity as well. So in special relativity, there is no mechanism of contraction or time dilation that can explain the physical fringe of a locally uniformly rotating interferometer in the light source that is attached to it. Relativists must ignore the explicit definition of what Einstein constitutes as an inertial frame, which was the entire premise of his special theory of relativity, and extending the closed polygonal circuit to claim that linear motion, can't be measured, right? So Sagnac went unanswered until 1917, and it wasn't answered until basically through Lorentz transformations. And even then, it couldn't explain the physical fringe displacement. It wasn't until 1918 that Paul Lavue came in to treat a uniformly rotating platform as a non-inertial frame and say that actually, because it's rotating, we have to treat it as acceleration. So we have to use general relativity and the equivalence principle to turn that rotation into a gravitational field, which I can use a metric tensor to conserve the conservation of that rotation into the gravitational field, and then say that that is generating local pockets of time dilation and length contraction of the apparatus to even begin to explain it. So the previous special relativistic derivations were kind of ignored, and it has to be looked at through the lens of general relativity. And also to note, general relativity explains it through a geometrically convenient transformation where they place themselves at the center of the rotating device as well, even though they claim that all frames are equally valid. And what that means is you should be able to special relativity should be able to derive the answer to this without a transformation to a reference, like to a geometrically convenient reference frame. If they're all equivalent, you should be able to derive it from the location, from the area on the disk in which the photographic recorder is located, right? You wouldn't have to choose the center every time to make it stationary and not rotating. All right, so we'll get into the Sagnac effect. So I kind of whiffed on the notes here, so that's unfortunate. 1 second.
I think it's probably Obsidian's fault. We can just blame that,
Yeah. 1 second. Almost there. Okay, cool. So here we have a citation from a paper by Nicholas, and I can't forget the year, but it's in the 80s, I think. But anyway, he goes down a list of 24 citations of the relativistic uh, derivation for the Sagnac effect as a special relativistic as an effect within special relativity. None of these papers or none of these answers adequately answer it, and they're all abandoned except for right here where the general solutions given. Yeah, citation 13. So this is Paul Lavue coming in to explain it with general relativity. So all 23 of these are all like, nah, dude, we can't use them. Don't talk about it. Hit up your boy Paul Lavue. So that's the only explanation that can be provided to that. So I traced down some of these citations and went through them all. And basically, what they do is they invoke well, actually, it's already included in the other slides. But what they do is they invoke a geometrically convenient position, and then they observe the non inertial frame, the rotating frame, and they go, okay, there's a time difference between the between the photographic recorder, that's a part of the rotating device, and the hypothetical inertial observer that they placed at the center of the device. They're saying that there's a time difference between these two, and this produces the fringe, even though the approximations given from special relativity cannot explain that as a physical effect. It's off by an insane order of magnitude, which we'll get into here in a second as we continue on here. Okay, so this is from A.G. Kelly, and he's breaking down that time difference that we were just talking about with the Sagnac effect and how they try to explain it through special relativity means and why it's inadequate to explain this first order effect of velocity creating a fringe proportional to that velocity directly. So Sagnac versus special relativity. The Sagnac effect and the effect calculated by the theory of special relativity are of different orders of magnitude. Special relativity stipulates that the time of a traveler, t prime, is slower than that of the stationary observer, time naught. So time naught is equal to t prime in times gamma, and that's your gamma correction. So that's going to be your length contraction time dilation correction. That'll give you the amount of time difference between these two, between the inertial observer and the non-inertial observer. Where t naught is the time for light to travel at a certain distance as measured in the stationary laboratory, t prime is the time for light to complete the same distance measured aboard the object traveling in a uniform relative speed of gamma equals 1 minus v squared over c squared to the 1/2. They're using a binomial expression. So we have here the coordinate transformation here of what they're doing. So DTR is the relativity time ratio. The Sagnac in the Sagnac case, T naught is the time of light signal to travel on a stationary circular disk, and T prime is to travel on the spinning disk in the direction of the spin according to the observer on the disk. So they give the full equation for that there. And then, so we have the ratio for DTS, so DT stationary and DTR. So DT stationary is the time difference for the stationary observer in relation to the time difference of the observer in rotation, right? So remember how I said they have to invoke a geometrically convenient position to watch the non-inertial observer violate special relativity, and then say that, and then base it on a time difference between the two. So let's see how that plays out. So it is shown here by Pogny in 1926, showing that the special relativity derivation is unable to explain the first order effect of rotational velocity, even though this effect is explicitly stated by Einstein that his equations would hold true in this frame. Notice that the ratio in this hypothetical scenario, the observer at the center of the rotating platform and the time difference between him and the photographic recorder, who is on the rotating platform but does not have the benefit of being considered stationary. From the stationary position, the distance traveled from the rotating platform, is preserved to explain the frequency shift. The frequency shift is the speed of light changing to produce the fringe. Remember, in special relativity, c equals c in all inertial frames. Again, we have a problem, or again, Here we attempt to explain this framework of absolute space and time, or I'm sorry, to explain the special relativity framework, we have to invoke absolute space and time to preserve the distance for the imaginary. Uh, so we can use the imaginary vectors to describe this time difference between an inertial observer and a stationary observer. The exact thing that we read in page 1 of Einstein's postulates of what he's not going to do and how he's going to replace it. He's like, no, we're not rolling like that, dog. We don't need to invoke that. We got you. Well, it's explicitly all based off of that. Without this, without violating its own postulates and prefaces, special relativity has completely failed on the face of it. Mechanistically, only the Æther model has failed to produce. The only thing the Æther model has failed to do is it's failed to produce evidence, a first order velocity measurement of Earth's orbital velocity. Right. So though the stationary Earth with respect to the rotating sky, that framework is remains unchallenged and still super viable. All right, according to me, but I'm biased because I believe in it, so whatever. Let's see here. So this is the modern explanations of the Sagnac effect, right? So this isn't just like the Nicklaus paper that was back in the day, right? Math's advanced and stuff since then, right? So maybe somebody else has figured it out. So let's see what Tartiglia in 2015 has to say about it. So to this day, there's still no derivation for it. They use the same geometrically convenient framework, and where they observe the linear rotation and the deviation in time between the two observers based on that rotation of the hypothetical observer. So the classic explanation, and even in the Tartaglia paper, right? So this is their explanation. This is their geometrically convenient thing after Lorentz transformation. The classic explanation is that the Sagnac effect can easily be described in classical terms if one assumes that the speed of light is constant with respect to a static ether. Consider that a rotating platform mentioned in the introduction that you see will no longer take will take longer to reach the light path at the emission point just at the rim of the platform. So again, the way that they're trying to describe it is that there's going to be a time difference. They don't really want to acknowledge the validity that the speed of light changes to produce the fringe. So they're still trying to describe it under the confines of a frequency change, which would be like a Doppler shift that they could analyze. But again, that's not going to produce the physical fringe pattern. That's just something you can analyze in the spectrum. That's not going to be the physical fringe displacement. Okay. All right. So then we have Barada's explanation here. So he goes on to say that, we'll explain this experiment by invoking a thought experiment. Well, that's not going to help us at all because Einstein's special relativity framework is based on thought experiments, and that didn't get us anywhere. We already falsified it on the face of it. But let's continue and see what their thought experiment has to say about it. So, hence the difference in the arrival times between the counter-propagating light rays is exactly the same in equation 8 is obtained in the lab frame. Oh, no way. So it turns out, the lab frame makes the prediction of the displacement for how much fringe there's going to be, right? And then you do the experiment, right? The rotating platform makes the exact same prediction based off of the exact same time and distances that you inputted in your equation to get the fringe shift displacement based on the velocity of the rotation. and you get a fringe shift pattern accordingly. What's the implication there right off the bat? That the time in the lab and the time on the rotating platform is the same. And if the time is the same for you, the inertial observer, right, you being stationary, and if time's the same on the rotating platform, if they make the same prediction and stuff, then the explanation given by special relativity that a hypothetical observer on the platform would measure a different time is untenable. It's completely illogical. How could you ever have that as an explanation when it's derived in the lab frame and it matches the prediction of the lab frame? The time is the same. There's no time displacement or time dilation or any time difference between the frames. That's not the component of what's happening there. So he goes on to say, though mathematically it is fine, but the physical understanding of the effect from the standpoint of the observer attending the rotation remains difficult. Yeah. So mathematically, they can thought experiment that where they're watching the rotation, but they can't explain the fringe pattern. This is so they didn't acknowledge that too hard in the Tartaglia one, but like they kind of beat around the bush about it. But in this one, they're like, yeah, it makes it explaining that component of it is extremely difficult. And by difficult, he means impossible, because this paper was in 2022 and there's still no answer for it. So here we have the conclusion to the paper. So we conclude that the origin of the Sagnac delay, or the phase difference of the Sagnac or Sagnac-like experiments, is in the non-midpoint of the measurement. So it's with respect to the non-midpoint of the measurement. On the arrival time difference of the counterpropagating beads leads to an unequal path travel traversed in opposite direction light rays of the interferometer. So no, the distance that makes the prediction that was derived in the light frame will measure the exact same on the rotating platform. So a hypothetical observer in there can't invoke absolute space as a change in comparative distances for the electromagnetic propagation between the two observers. Another untenable facet of relativity that like how they're trying to explain a simple rotating device, as Toby puts it, man. Simple locally rotating interferometer. So they can't explain any of that. How will they explain a giant stationary interferometer, I wonder? So we're going to move on to Michelson Gale Pearson now. So this is a closed loop setup, similar to a Sagnac. I'm not going to go all the way back, but similar to the Sagnac setup, where a light beam is split into two counter propagating directions, and then it recombines after it completes a loop. So the dimensions of this was about 1 kilometer. So they had made like a giant rectangle, 1 kilometer long, and began their experiments. So this is a first order setup, this closed loop. The split beam, clockwise and counterclockwise beam, completes a circuit at the start of the loop. So the mathematical derivation here that they give, derivation that they give is, let's see here. So they say that the effect of rotation of Earth on the velocity of light is derived from a hypothesis of a fixed ether. So this is 1925, and this is the Michelson Gale Pearson experiment. So the expression for the time difference between the two interferometers, the clock of the two fringe pencils, one of which travels clockwise and the other counterclockwise in the direction, may be deduced on the hypothesis of a fixed ether, where L is the path length at the latitude, L sub 1 and L sub 2 are the latitude, blah, 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 and corresponding linear velocities of Earth's rotation. V is the velocity of light. So they're basically taking the two counter propagating beams, and they're measuring the French shift, right? They're coming up with how they're deriving the French shift based off of here's the full component. Here's the full breakdown, a better breakdown of it. So we have delta equals 4a omega sine pi or sine phi over lambda v, right? So what is this? So delta is the displacement fringes. So this is going to be how much fringe is going to be displaced. Is going to be equal to the 4 times the area in square kilometers of the apparatus. So the path that light has to travel times the latitude times over the velocity of light times the wavelength. Oh, the angular velocity is included in the area. Sorry, I read that kind of out of order. But anyway, when they put in the sidereal rotation, and they put in the latitude, and they put in the wavelength of light that was used, and the speed of propagation, right, that fixed speed, they get a fringe displacement that corresponds to sidereal time. So no measurements of Earth's orbital component of 30 kilometers a second, but they have an angular velocity, right? So remember, the translational speed measured in the orthogonal setups is around 6,000 to 10,000 kilometers a second. Now, the Earth is supposed to be rotating at 1,000 miles per hour at the equator. So we can't have the linear interferometry measurements overlapping with the closed loop setups that are supposed to be measuring only angular rotation, right? So they look at this fringe displacement as a rotational effect, and they say that it's due to Earth's rotation. Now, remember, our boy Einstein says we don't need no stinking absolute space. We don't need to introduce imaginary vectors for electromagnetic propagation to occur. So they don't derive it through the lens of invoking that geometrically convenient position Actually, they do. They go to the center of the Earth, but that's a whole nother thing. The mechanism by which they say that this is measured is because Earth's magnetic field is being carried with the rotation, and that's giving a boost to the electromagnetic propagation such that it's causing a fringe shift pattern that corresponds to sidereal time. And then in the inverse, when it's going the opposite direction, they say it's going against that field. So that's the mechanism provided to explain Michelson-Gale-Pearson as a special relativistic effect. Earth's magnetic field is actually dragging it. And then they actually went as far as to say that a stationary ether prediction would actually be falsified if there's a fringe shift pattern measured due to the velocity component, because like the way that they're trying to talk about the ether as if it's static and stationary, they say that the ether would be entrained with Earth's rotation. It would get trapped in the tube and it would bounce around, and it would cause it would cancel out the rotation. So they say that the prediction of motion for ether is that there's going to be no fringe, and that the relativistic prediction is that there will be a fringe displacement, dude. Like, they flipped it so hard to get this to get ahead of this, to get this explanation out, because it's crazy. So we'll move on here and we'll do a quick recap. So the independent variables will be the orientation of the apparatus, how it was constructed, right? And then the other variable will be the mediums of the tubes. So they used a vacuum, and then they also used helium and some other thing I can't remember, but they were using that to like kind of to calibrate it, essentially, right? To figure out what they were getting measurements of. And then the dependent variable would be your fringe again. And then the result, the fringe was proportional to an angular velocity of 15 degrees per hour, which happens to match, with sidereal time.
Bro,
All right.
can I say one thing real quick?
Nah, I want to get this done.
All right.
Sorry, I'm super close. So Miller. So now we're going to get into the continuation of the orthogonal setups. So we have the Michelson-Morley experiment, where they did 6 days of interferometry readings and redefined all of physics based off of that. And you would think maybe they would want to have a guy on the back end of that doing some continued exploration to make sure that they didn't make a mistake or whatever, right? So Dave Miller came along and continued the orthogonal interferometer setups. He even inherited the original Michelson-Morley setup. He constructed several of his own interferometers, and in doing that, he came up with different shielding methods for to protect the path that light's traveling on, how to shield it from thermal conditions, what materials to even shield it with to prevent the ether wind from being blocked by dielectric materials or Fermi surfaces like metals and stuff, right? So like all of these things affect the ether wind, which affects the readings in the interferometer. And Miller spent 30 years of experimenting to figure all this out and document it and go over it. So we're going to kind of touch on his work, go over what he measured, and then continue on with the history here and wrap up. So we got Dayton Miller, 1902 to 1933, continued linear interferometry experiments, and up to and including doing them at different altitudes, sea levels, in basements, and in different shelters, different housings for the interferometer, right? And how that would affect the readings. And it turns out all of these factors contribute to the readings, and you have to take them into consideration when you take the measurements. So summary for 30 years. Yeah, let's see. Did that applying the changes? Okay, so Miller discovered through analysis that he was measuring sidereal fluctuations that change. So the fringe shift patterns that he's measuring change with sidereal time, and where they reach their minimum and maximum dimensions, actually according to the equinoxes too. So we have this measurement where they say we can't measure Earth's orbital velocity or any of those components, but we're measuring fluctuations that have to do with the sky, but just not at the velocity magnitude that they need for heliocentrism. So what's going on there? Can they measure linear interferometry? Or can they measure linear motion? Can they not? What's going on here? It's going to get crazy. So we got some setups here of these are just some pictures of the interferometer setup that Miller used in different housings. So this one was on Mount Wilson. So he uses protective insulation removed from this photograph. So he had a case to go over top of it to protect from thermal and wind and stuff like that. Let's see. And here's another picture of it. So, right. Here's the Mount Wilson Observatory. Shout out to Mount Wilson. So the optimal housing should be for the interferometer that Miller figured out was that it should be kind of open and free flowing. The thermal insulation shouldn't be using any dielectric materials or any metals, Fermi surfaces. Okay, so when we get into his measurements, these are the measurements that he found with the minimum and maximum dimensions reaching on the equinoxes. So the speed of light is changing proportional to the equinoxes somehow, right? How is that happening? So what Miller plot? So when you plot Miller's data out, what he thought he measured, or his interpretation of what he measured, was Earth's orbital motion. But for some reason, he couldn't explain why the readings didn't give a 30 kilometers a second. So he was totally fine with that. He was like, "Look, man, these are the measurements. This is what I believe we're orbiting, and these are the measurements I get, and these are the times a year that when these measurements show their fluctuation." So how they say that the Earth's on an elliptical path and how it would have to change speeds 4 times a year to meet that orbit, but they say no, we can't measure it, not sensitive enough, blah blah blah, right? Well, this is what they measured, but they don't accept it because it doesn't give that proportional velocity component. Because when you get into how interferometry works, how there's a proportional velocity component to velocity that can be extrapolated from the speed of light through fringe patterns, it becomes glaringly obvious that the second order explanation of length contraction and time dilation is actually superfluous, right? Superfluous, right? That's the one that's unnecessary. That's the one that can't explain anything, because the measurements do give a velocity component, right? So they they can't explain. They can't have both of them. So that's why they throw Miller to the curb. But Miller wasn't a punk though. Like, he knew how to handle himself. He just kept doing experiments. Anytime criticisms were addressed, he would just go through and do more experiments, do more data, and he made it clear in his publications what he was measuring and how he separated that measurement from his interpretation of what he thought was being measured and stuff. So you can actually go back through Miller's work, look at the periodicity of what he was measuring, see the effects, and know that it's separate from his interpretation of of how he was applying the measurements, mapping it through sidereal time and then applying a directionality to it and saying, like, we're traveling in this direction and all that. All second order interpretations, right? Those are all that's all Miller's understanding and Miller's application of it, right? You don't have to adopt that whole framework. We have the first order measurements. We can apply our own interpretation from there, right? All right, so we're going to move on now to Yuri Galev, who reproduced Miller's work, because a big part of Miller's work was that the readings that he got fluctuated at altitude. So the original Michelson-Morley experiment was done in Cleveland. It got a translational speed of about 6,000 kilometers a second. Now, Miller started doing his interferometry experiments and got similar readings at around the same altitude. And when he went to Mount Wilson, which is 1,800 feet above sea level, he got stronger readings. That's where the readings jumped to about 8 to 10 kilometers a second, depending on how you read them. So that's where you get that increase. So he was like, okay, so there's a increase as you go to altitude. So this was a huge thing that Miller had discovered, and this is a direct refutation to relativity theory and the interpretation of the cosmos, essentially, right? Because remember, they've got proportional velocities, with stellar aberration based off of these ratios, and it's like, if it changes at altitude, well, that doesn't help. That can't explain anything. The implications immediately stop going outward in infinite space and become inwards, where we're stationary and the sky above us is causing these things, right? So Like it's like a trickle down effect. That's why they can't have any of it. So so we'll get into Yuri Galev now, and he reproduced those works. So he also measured that sidereal fluctuation, and he also measured in a vertical motion gradient against the velocity increases at altitude. So we'll get into how he made these measurements. Okay, so this is from Galev's paper. The purpose of this work is to experimentally verify in optical wave range the hypothesis of the existence of the ether in nature, a material medium responsible for the propagation of electromagnetic waves. The second goal of this work is to measure the kinematic viscosity of the ether. Thus, the present work is a logical continuation of the studies carried out in the radio wave. So he also did the radio wave stuff, which we'll cover on the back of this. Okay. So this is the setup for his interferometer, which I'll show you a better topographical view in the next slide here. But this is what the interferometer looked like. So he has a shielded side here. That's closed, or no, I'm sorry, not closed. He has a shielded side here where the beam goes through, and he has an open side here. So what he's going to do here with this setup is show how electromagnetic or how the ether wind responds as to fluid dynamics. And I'll get into what that means here in a second. So here's the topographical view again. We have the light source, beam splitter. Beam gets split in two directions. Two directions and recombined over here. And then again, we have this one's going to be our tube. And what he's going to do is he's going to rotate the interferometer and measure the displacement based off of how long it takes for the interference pattern to settle down. Right. He's going to extrapolate a laminar flow and a turbulent flow out of this interference pattern based off of the wave bands and when they settle, like the movement of the wave band. So let's see. So part of the tube. Okay. So to kind of recap here, the tube is placed into a gas stream, right? So like if you think of the ether stream like a gas stream, you would have the interferometer is accepting the flow through the gas stream in this orientation, right? But if you were to turn the interferometer perpendicular to that flow, the ether would be hitting the side of the tube and it wouldn't be flowing through it. Does that kind of make sense? So what he's going to do here is he's going to take this interferometer in different orientations. He's going to turn it. And when it turns, there's going to be the waveband that he's monitoring, right? The fringe shift pattern is just going to move across the screen rapidly in different directions, right? And when it settles, it's going to determine that is when it's going to be when the flow goes from turbulent to laminar, right? When it goes laminar, the ether wind, like the what you would consider like the molecular structure of it, right? The individual particles, right? Which it's not what it is, but it's just how he's modeling it. That would be when those are flowing cohesively and they're not being disruptive to the flow. Right now in the turbulent flow, they're going to be chaotic and bouncing around, and that's going to cause a difference in flow. It's going to cause the variation, the fluctuations that he sees in the wave bands. So he's saying that if the ether is a gaseous medium, it'll respond in that electromagnetic propagation through it will respond in the same way that can be described through fluid dynamics using the equations that describe fluid dynamics. So like the actual relationship of how fluids and gases interact with material mediums. He's saying he can measure that interaction based off of the fringe pattern. So we'll get into that. So he came up with a coefficient here to when the displacement goes from tubular to laminar. So when the wave bands go from chaotic displacement and an irregularity, right? When they settle down to regular and become stable, he has a time threshold set for that. And when it reaches 0.95, that's when he determines, okay, it's laminar now. It's a steady flow. So again, changing the orientation of the device is going to affect the laminar flow in the laminar flow of ether through the apparatus, which is going to affect the fringe readings. So that's the premise of how he's measuring it, and that's the kinematic viscosity of the ether that he's measuring. These are the effects that he's measuring with this, right? So see the graph above see, in the graph above, the transition from turbulent to laminar flow occurred at the threshold of 0.095, signifying when it's reached its steady flow. Galev utilized the wave bands to discern the laminar flow and turbulent flow by observing the interference fringes produced by the gas in the tube. The laminar flow resulted in consistent and predictable fringes, while the turbulent flow exhibited irregular and fluctuating patterns. By relating these patterns to the hydrodynamic equations and mapping the relationship between the wave bands and where they align when the apparatus is parallel and perpendicular to the ether wind, Galev effectively measured the kinematic viscosity of the background medium necessary for electromagnetic propagation. So if we recall back to the criteria earlier, where we had a space effect, an anisotropy effect, a height effect, a cosmic effect, and a hydroaerodynamic effect. Well, this these equations describe that describes that turbulent and laminar flow of the fringes. That satisfies the conditions of the hydroaerodynamic effect. Someone's mic's going off. Please mute. That satisfies those conditions right there. So let's see. Additionally, to test the viscosity, there would be and then so we'll get into satisfying that the hydrodynamic component with another aspect of it, which will be that if the ether is like a fluid-like medium, that the translation of motion, it will produce a vertical motion gradient that will get stronger at altitude, right? Because it's closer to the source of what's rotating, right? So it'll have a stronger translation of motion there. So there's the readings that Galev took, and we'll see the comparison to Mount Wilson here. So we have Kharkov's daily periodicity, two different years, so two different measurements. One's the wave bands, and then the other one is the radio link experiment that we're going to go over here in a minute. So, and then the other one is Mount Wilson. So that's Miller doing his runs, and we're seeing the exact same pattern from 1925 all the way to 1998 and 2000, same times a year, same periodicity of the events. So here we have the let's see. So Miller's results were reproduced. The daily fluctuations observed in the ether drift velocity align with sidereal time and exhibit a minimum and maximum fluctuation dimensions. Minimum and maximum fluctuation dimensions that correspond with sidereal time. So backing up Miller's findings. So we have a first order effect, first order measurement, and a first order analysis from Galev's work. Let's see. And then, so we can really kind of draw that relationship between that turbulent and laminar flow. It's a really solid way to get the reading. So like we often say things like, show me a bucket of space-time, or how do you manipulate space-time, and all these things, right? Well, it's just empty-handed. Nobody has anything. It's like, well, show me the ether. What's the ether? What do you do with it? Well, here's an effect that we're observing that is eloquently described as a gaseous that's eloquently described by a gaseous medium and how it interacts with dielectric dielectric insulators and Fermi surfaces, right? So it's a way more meaningful relationship, I would say, than just an empty equation that describes an abstract phenomenon in the sky that you can't do any meaningful independent or dependent manipulation with, right? Can't manipulate any of the independence with it. Can't do any controls on it, right? So you're just kind of taking their word for it. But with this, we actually have, like a causal mechanism, a fluctuation in the speed of light due to XYZ factors. And we can show first order effects, first order measurements of it. We can get into first order approximations and second order approximations and break these things down without disregarding the first order measurement itself and getting lost in second order abstractions of the measurement to try and explain it. Right? Okay. So this is the radio link setup here that Galev did. So this is a 13-mile distance. It was line of sight propagation. Here's a here's a side view angle of what we're looking at over here from the top view. All right. So, and he has different reflector points along the path here, where he can take like horizontal propagation readings of the speed of light at that altitude, so to speak. So he can you can measure that gradient really precisely. And the way that this setup actually works, it's really cool because the A the A emitter has a source and receiver, and B has a source and receiver. So what he's doing there is it's taking like a one-way measurement going from A to B and B to A. So he's got like a cross pattern diamond grid formation over this 13-mile distance here. So the gradient that he's measuring there is just like he's got a whole what would you call it? Like a whole field set up essentially, where he can get these measurements done. So here's a graph of the measurements when they're plotted out. So we get a symmetrical periodicity for the propagation going from A to B and going from B to A, symmetrical. So this is beyond the scope of like what would you say, like Earth rotation, atmospheric conditions, anything like that. Like it's the fact that it's symmetrical is crazy. And then when you get into the periodicity of the events here, you can see that they match. Like there's no that's just C fluctuating based on sidereal time, based on that that galactic component, right? For some reason. So we have here, so the symmetrical readings in the east-west and west-east due to the gradient of the readings, the gradient value of the ether wind speed, GWRK, measured at 6.7 or 6.4 kilometers a second. So that was where they matched the Cleveland's data, right? So that was the first Michelson-Morley, the 1887. I'm sorry, that was the second Michelson-Morley, the 1887 one in Cleveland, where he matched the same speed all across the world, right, at a different location. So we have 3 data points, right? We have Kharkov, Mount Wilson, and Cleveland, where we can build an altitude gradient for these measurements and plot out, how the speed fluctuates at altitude, right? The sidereal fluctuations reaching their minimum and maximum dimensions, and then within diurnal time, there's fluctuations within them. So what they were saying there is that for some reason, like all these cosmic effects keep showing up in the periodicity of the measurements. So to end on the graph there, we have column 2 representing the value of GWK, which is what was that? That was the ether wind speed at Kharkov. We have the ether wind speed, the horizontal component of the sidereal, the ether wind derived from calculations estimated from equation 42. So that was where he was approximating or linking the Miller data to his measurements. So he was coming up with that. And then this represents the value of the MDK. So this is combining them all, adapted at the Mount Wilson. So he just goes over. It's basically just a comparison of the gradient of the 3 locations, right? So it's just adding them all up and showing that gradient. All right. So what do we have? What's going on here? We have the first order velocity effects, a velocity gradient measure that increases at altitude. We have first order measurements, the radio link up configured to take one-way measurements. All the other measurements from the previous setup from Gallup as well. So the independent variable would be the geographic latitude, the altitude, dielectric materials used during the readings, like literally all the same stuff that Miller did essentially. And the dependent variable would be the fringe shift produced by the velocity gradient and the first order mathematical analysis used in the equations to make dynamic predictions. So again, he didn't just use kinematic equations. He didn't use hypothetical equations to describe that hydroaerodynamic relationship with the turbulent and laminar flow described by the wave bands when reorientating the device parallel and perpendicular to the flow of ether. He used real actual equations that are used to describe the flow of material medium and its interaction with material medium. All right. Any questions, comments, or concerns? That's everything, boys.
Got black screen right now. Oh, there we go.
Yep.
Bro, thank you for that, Alan. That was great. Is there a way you could go back to that slide with the delta representing the number of fringes and the equation like 20 slides ago?
Oh, yeah. From Nicholson Gale. second.
It's like
No.
delta equals a big thing.
There's no real
over
way to navigate in Obsidian, is
B
there?
on the bottom in the denominator. There was a.
Yeah, it's coming up. I'll get it. I
The
believe.
only thing the Æther has failed to provide or failed to do is provide first order measurements of orbital velocity.
Isn't
Yeah,
it the quote of the fucking century right there?
Yeah.
so right
dude.
here,
that one made it right square in the middle of my notes.
the delta and the V, you can just like exchange those. You can put the V over on the left and the delta on the right in the denominator, and you can just plug in how many fringes you counted and get the literal direct velocity of light.
Yeah. Funny that they had to figure that out before they had to employ it to obfuscate it in the first place, though, huh? That was interesting.
It's awesome.
Also,
and then omega wouldn't be the angular velocity of the Earth; it would be the angular velocity of the sky. And then
Yeah.
I don't know what A would be, what the counterpart to A would be, because it says the area in square kilometers. I don't know what the area is that it's talking about.
Yeah, the area that it's talking about is always the area that the path that light has to take, right? So like the full duration.
Okay.
So if it's so you can think of it if it's something like a coiled loop or whatever, like a fiber loop, and it's coiled, but the cable's 1,000 kilometer or 1,000 meters long, then your area is 1,000 meters. Does that make sense?
Okay. Yeah. Except 1,000 meters is not square.
It doesn't matter. You can do area or length. It's the same.
Oh, okay.
Now that we're noticing where that came from, every formula that I've seen has to denote the proportional relationship to V, doesn't it? Like, holy crap, it's everywhere.
Everywhere.
Yep. Everywhere.
There's a proportional relationship between fringes and velocity of light.
No
Mhm.
shit. It's like a literal relationship that's been right in front of us. They've been using it to like beat us over the head since we started. Damn.
Man, I thought it was funny when you were talking about MGP, Mickelson Gill Pearson. You talked about the magnetic field thing. It occurred to me it's like hilarious how they use it against the field, like they reference the magnetic field, how it's proportional to that, and it's funny
No,
how
dude.
it's like
Yeah.
hilariously convenient that they don't have a proper definition of a magnetic field, so they can like, well, we're just assigning a point in a mathematical construct, so we're not actually doing what Einstein said we can't do.
God.
Man.
That's
Yeah.
hilarious.
Sorry, guys. Dang. I'm going to mute.
And so with Ares' failure, did they ever come up with a relativistic explanation for it? Because
Never.
Because don't they, in order to get away with their explanation for Ares' failure back in the day, they basically had to invoke a static ether, right? So I don't like between the two of them, it's like totally incongruent. It seems really bad for them.
Well, so the static ether was a direct result of that discovery, right? Oh, we didn't correctly deduce what we know to be the motion of the Earth. Therefore, we must amend our next experiment to accommodate your failure. Something like that, right? But of course, opposite of that.
Yeah, dude. Dude. It's so funny that they took the ether prediction and was like, nope, that's the relativistic prediction. And then they said that the ether prediction was actually no fringe, bro.
Yeah, that was hilarious. too.
I died laughing when I read that. I'm like, who are you people?
Dude, all the
you-
things you have to do to lie about everything to get what you want, man.
Dude, so crazy. Yeah.
Imagine, like, hey, actually, we live on a flat plane, but we're going to convert all the measurements and things to a spherical coordinate system. We're going to do some transformations. Don't worry about that. We have to correct it back to the thing, and then we're going to put it back, and that's how it is. And you're like, yeah, but could you just not do any of that and put it in the first frame, though?
Notice what else happens. I don't know if anybody was hearing me talk in Geo's channel earlier about the wavelength compared to the frequency shift, but if you swapped delta for lambda and you kept V constant as C, like you kept it as a constant C, then you would see a wavelength shift. You would represent it as a wavelength shift. So, like the
wavelength
amplitude
shift
of the wave. Yeah.
You know, I'm thinking like how you'd mathematically apply a Lorentz transformation, which is derived from how you'd apply like those whatever he stole it from before that when they were trying to figure out how to scale a Doppler shift thing. So when you're applying that transformation, it's always the same structure, right? Like a Scanslail.
Alan, that was awesome,
Like a
by the way.
scalar
That
coin.
was one of the better presentations I've seen on this topic, man. That was really succinct. You really hit on everything. I don't know. I guess these presentations just keep getting better and better as we keep learning more and
Also,
more. But you really did a fantastic job, man.
Thank you, man.
yeah,
Appreciate it.
think
Yeah, if
bigger
there's
and bigger. I
no
think.
yeah, dude, yeah, I had to hit up 92 slides, bro. So if there's no questions, comments, concerns, or whatever, I'm gonna go ahead and tap it out.
Nothing here. I made my comments. Anyone else?
We're gonna have to use this to beat them over the head with, right? When they don't understand why they can't apply relativistic corrections to second order measurements, when they're taking all sorts of things, they're like, "No, I have to apply a Lorentz transformation." Okay,
Oh,
let's
dude,
get you out of your head and figure out why you think that dumb shit. Let's just look at some, you know what I mean? So this has got to be fundamental to transforming them, I think.
yep, absolutely. I'll be right back. I'm gonna roll the outro.
Cool. I'm going to go ahead and close out the stream on Ether Cosmology as well. Everyone tuning in, thank you so much for taking your time to learn with us tonight. And we will see you on Thursday for reading night or research night, where we will be discussing tides, led by Shane, or researching tides. I believe Shane's going to bring a paper or two for us to go through. And then next Tuesday, don't forget, be ready for LIGO night. Yay! All right, for real.
It's so
Next
funny.
Tuesday, LIGO night, we're going to talk about LIGO and what they measure there, or maybe don't actually measure, but compute.